process, collect, and distribute that data. And I stole that nice definition from Wikipedia. So why is it important in solar car racing? Say solar car racing is a series of decisions. When you design a car, you have to make decisions. Are you going to do a 3-wheel car, or a 4-wheel car? Are you going to have a 96-volt battery or a 48-volt battery? What type of cells are you going to use? Are you going to use a chain drive? Are you going to use a belt drive? Are you going to do a direct drive? Once you get to the race, you still have decisions to make. Who's going to drive your car on a given day? Are you going to wait out rain? Are you going to go ahead? What speed are you going to run? Are you going to stop and charge, or are you going to run? Are you going to try to get ahead of the weather? See, good information allows for good decisions. To give you a quick story from 2 years ago, the last day of the race was a miserable, miserable day. It was rainy and cold, nasty, and we were to the point we were just about considering calling off the race for the day. And we had one team that was fairly far ahead, and the second team, they decided they were going to run out ahead and try to get ahead of the weather and get some miles in. The other team decided they were going to sit at the start line. They had a meteorologist on staff, so they'd gone through and collected all the weather information. They had the different weather models, and they were able to make a decision to sit and stay and wait out the weather. If they had decided to go ahead, if it had been reversed and the other team had decided to stay and they had gone ahead, it would have changed the outcome of the race. So good information leads to good decision making, and that's what we're here to do. Okay, and you can't have anything without a ubiquitous sports analogy. I will admit that I know nothing about sports, and I'm probably the worst person to use this one, but we're going to do it anyway. So football, most people are familiar with. American football, because we have British and not soccer. So, you're on 4th and inches. You're the coach, you make the decision. Do you go for it or do you punt? So what do you want to know in order to make that decision? Do you have anything you want to know?
Where you are on the field.
Where you are on the field, very important. Okay, ball's on the 30-yard line, so you have one piece of information. Anything else you'd like to know?
What's the score?
Oh, score, time. Okay, well, after the next one, your team has a 50% conversion rate. Okay, that may or may not help you make that information. But that's a piece of information that you don't just know. You cannot look at your team and say intrinsically that I know that I have a 50% conversion rate. You've tracked data, you've kept records, you've analyzed records in order to come to that piece of information. It's not something intrinsically you can look at and see. Your field goal kicker is 70% from the 30-yard line. Again, you can't look at your field goal kicker and know that. You have to have had data, tracked it, analyzed it. And same thing. The opposing team has never stopped a conversion all year. That's a really important piece of information. And I bet having that piece of information would drive the decision that you're going to make. So having good information would lead you to make a good decision. Whereas if you didn't, it would have been a toss-up. You could have also flipped a coin. It might have worked out, it might have not.
What's the score?
I forgot the score. Again, not a sports guy, so. So, again, I'm a naval officer. I like good military quotes. Sun Tzu, 4th century Chinese general. If you know the enemy and you know yourself, you need not fear the results of 100 battles. If you know yourself but not the enemy, your victory gained you will also be sure suffer defeat. If you know neither the enemy nor yourself, you will succumb in every battle. So, solar car, know your enemy. So there are many places to gather information. One of them which is you're probably very familiar with, Solar Car Challenge website. So, we want to know what it's going to take. Most people here are going to want to win the race. What's it going to take to win the race? So we have some data from the Solar Car Challenge website, freely available information. This is 2016 results, and I did this for the closed track events, a little analysis. We have 2016, as you can see, we've got results up there going back to 1995. So collected some data. Nice little Excel table. So now we're going to do some analysis on it. We did a basic variable plot. We know that the minimum number of miles to win the Solar Car Challenge, 361, back in 1996. The maximum there was, in 2009, was 831. Average is about 597 miles. And the mean's 649. Well, so what does that mean? If you're aiming to win the Solar Car Challenge, you can project out forward and figure it out. what you might think you might need to win. So if this trend continues, in 2019, the next closed track event, you would expect 847 miles to win. So what are you going to do with that information? If you average it out with our race periods, 847 miles means you need to maintain an average of 26 miles per hour. So if you maintain a constant pace of 26 miles per hour for the entire race, we think you should reasonably win. Okay, that's a great piece of information, but what do you do with it? That can drive decisions on things like gearing. If you're gearing your car to go 60 miles an hour, that might not be the best idea. You really might not need to do that. If you can't maintain 26 miles an hour, you think you might want to change it a little more. So this analysis was actually done last year. Turns out I was actually wrong. As you can see, the last point went down this year. And something really screwed up with my graphics. But anyway, that line's supposed to be lower. So based on last year's results, we're thinking more like 735 miles. So again, that can drive decisions. And I'm not saying it absolutely should, but that is a piece of information that you can keep in the back of your mind as you're making decisions on what the requirements are that you place on your solar car. Okay, know yourself. By the nature of solar car racing, you have a limited amount of energy. We are an efficiency contest. You start with a certain amount of energy in your battery, you're limited by what you can take in and what you expend. For most solar cars, energy usage is proportional to speed. At low speeds, it's a linear progression. So the faster you go, speed goes up linearly. There's a certain point, based on the aerodynamics of your car, that speed starts going up exponentially. So at 25 miles an hour, you might be using 10 amps. At 26 miles an hour, you might be using 30 amps. If 1 mile an hour might not make that much difference in how far you get in an hour, well, it's going to make 1 mile. But that difference in amps could be very substantial. So if you know your car and understand how your car works, you can make good decisions on where you drive. And I also do consulting for both high school teams and I've done college teams. So I've had access to a lot of people's data. I've had access to Houston's data, I've had access to MIT's data, and I still have access to Georgia Tech's data. I have seen 2 different people drive the exact same race course on the same day within 15 to 20 minutes of each other. I've seen those 2 people use vastly different amount of energy to the order of almost 50%. So if you don't know how you're driving, and if you don't understand how your drivers, who your drivers are, what their strengths and weaknesses are, you're putting yourself at a massive disadvantage. Know yourself. Okay, so how do we get to the know yourself part? The first and most important thing you can do is drive your car. Way too many people show up with their car, the first time they drive it is on the track at the Texas Motor Speedway. That is the worst thing you can do. We've said for many years, the car that has the most miles on it when it shows up at the race is likely going to be the one that wins. Not because it's the best car, or the best design, or they did the best work, but they generally know their car. They understand these things of driver selection, speed selection, things like that, how to change batteries, when to change batteries. And with that, driving your car, you need to know what happened while you drive your car. We use that using telemetry systems, which we're going to talk about here in a second. So telemetry is a system. It's not, we talk about telemetry being a piece of hardware. Telemetry is actually a system. The hardware is just a dumb piece of silicone. It can't tell you anything in and of itself. You need to tell it what you want to know. So the first thing you do is choose the data you're interested in. Once you know what you're interested in, you start looking for sensors and systems in order to gather that data. We tend to think of things like multimeters, amp meters. It might be the internet, it might be a meteorologist. Those are all pieces of information that fuse together to make a full picture of what's going on with you and your car. Once you have that data, you figure out how to record it, then you process it. Data is just data until you do something with it. I was accused, Michael called me bad names many years ago because I love data. You can give me as much data as you want. I absolutely love it. But having all this data is absolutely meaningless unless you know what it means, unless you can do something with it. And in order to do that, you have to process it in some way. And then you want to display it because obviously you want to be able to see it. And then you need to do something with it, which is make good decisions. You might notice there's a mantra here, is make good decisions. Okay, so I gave this presentation last year. 30 minutes before the presentation, I sat down and wrote a list of the things that you could potentially measure on a solar car, things that I would be interested in as an engineer and an experienced solar car racer. This is a very extensive list. Not all of this is important to everyone. In fact, most of this is probably not relevant to most people. But it's just an example of the number of things that you could be interested in. And you can take pictures of it. This is on the website and will be available.
Is on the website.
Is on the website. So it might be easier to read that way. So, and I'm not going to go through all of them, but a couple of the important ones, the basic ones. Your battery voltage, very important. If you're running a lithium-ion car, at a certain point, your batteries explode. I don't think I need to really emphasize that's a bad thing. I'm also one of the troubleshooters for the race, so when things go badly, we don't fix your car. However, we are an educational organization, and we will help you troubleshoot it. And I'm one of the people that gets pointed out to go help you do a systematic walkthrough of how you troubleshoot. The most heartbreaking thing I do in that role is help teams figure out that their batteries are completely shot. Your standard lead-acid battery, if it goes below 10 volts, is not coming back. And I sat with at least 4 teams in the last 5 years as they went through the process of figuring out that their battery pack is shot and their race is done. And that is something that is absolutely heartbreaking as a staff member and as someone who loves solar car racing and enjoys this. So it's one of those things that I think is important, to know what your battery voltage is. Your amp hours. Amp hours, voltage kind of gives you an indication of the health of the battery. Amp hours are your fuel gauge. They tell you how much energy you've actually put in or taken out of that battery. Very important. Some of the other things, if you wanted to be very advanced, these are some of the college level stuff. My college team, we had a model of our solar car. We measured how much energy we expected to use based on the weight of the driver, the terrain we were going to use. You can do some of that really interesting stuff. Probably not applicable to most people, but just some of the things on the list and some of the things you can do. Sorry, my computer's locked up. Okay, so from this list, you're going to pick a certain number of sensors that you're interested in, or a certain number of data points that you're interested in. From there, you're going to start picking sensors that you're going to use to measure this. And I just picked a random selection of sensors. We have the current shunt. These are Hall effects sensors, so basically you don't have to have a high voltage contact. They basically clamp onto the DC wire and can use it. We got a GPS antenna. We have a really basic potentiometer. If you want to measure the position of the steering wheel or the brake pedal or the gas pedal, a very simple potentiometer is good. And we've got a linear potentiometer, and that's a little proximity sensor. Nothing particularly exciting in there. But when you pick a sensor, there's some vocabulary that you need to be concerned of. You have the range of the sensor, sensitivity / resolution, the precision, and the accuracy of the sensor. So the range of the sensor is the amount of readings it's designed to measure. So a voltage sensor might be good from 0 to 12 volts. That sensor is not going to be very helpful if you're trying to read 24 volts. Same thing with a pressure, if you want to measure tire pressure. A sensor that has a range to read 3,000 psi might not be the most effective if you're trying to read a 30 psi tire. So sensitivity, plus the resolution. It's an absolute quality that's inherent in the system. It is the smallest amount that sensor can measure. So, for example, I'm going to show you my telemetry system here in a few minutes. It goes out, my voltage at one point was going out to 12 decimal places. Well, my sensor is only good to 1,000th. So basically anything beyond 3 decimal places was just noise. So there's no point in having that. So you have to know what the information sensor is good and what the sensitivity of it is. And the precision is how repeatable the measure is. That's telling you that if the sensor says you have a 12 volts, that it's actually 12 volts. And the accuracy. Or sorry, I'm screwed up accuracy. Precision accuracy. Precision is the repeatability. So if you measure 12 volts, each time you measure 12 volts, you want to say 12 volts. You won't want to say 12 volt one time, 12 and a half the next time, 11 and a half the next time. Accuracy is how accurate it is. It is exactly 12 volts. And this is best described with a target. This is one way you most often see this described. So this is a target. Do you think that's accurate or precise?
Accurate.
I heard the right answer. I don't think that's either. So that is a low accuracy, low precision shooting. So how about that?
Precise.
That's precise. So precise is good. Well, yes, that is precise but not accurate. So the nice thing about accuracy is you can correct for accuracy. You can make an adjustment in your software and say, okay, subtract 2 inches and move right 2 inches. And if you're precise and you know that you're hitting that every time, you can make it accurate if you know where it is. So how about this one?
Accurate.
Yeah. So that is high accuracy, low precision. We're around the target, or around the bullseye there, but we're not getting the same thing every time. And that can be frustrating as you don't know exactly what your system is actually doing. And this is the holy grail. We have a highly accurate, highly precise system. Okay, so data processing. Now that you've identified what you want you're interested in, you figured out how you're measuring it, you've collected your data, you're going to have to do something with it. So this is the problem with data. This is the actual scoring results for the 2016 race. Does anyone have any clue what that says?
Yes.
Yeah.
It's a number larger than 7.
Yeah, I kind of figured out, we're dealing with Walnut here. Christian's the judge, but that's... Hi, Christian.
It's your fault.
Yes.
You're trailering.
This is, again, where data by itself, without processing, can be fairly useless. This doesn't tell you anything. Okay, so with just a little bit of formatting, that became a lot easier to read. Now we really can figure out, oh, we have a number here, that means something. To us, that means that's the tablet that we're recording it. Oh, we have a date. We have a timestamp. We have the position. We have a bearing, which I don't know why we had in there, but we did. There were required trailing.
More data.
What?
More data.
More data. Yeah, that's my fault. Then we have speed, so a little bit better. Same thing with a little color, even better. That's much easier to read. For the little headings, we actually know what we're talking about. And then I don't have the slide I really wanted, which had the track as a visual picture. But so that's one way to display the data. That's displaying raw data. That may not be the most useful way to look at your data. It's great to know that your tire is at 12 psi. Okay, that may or may not tell you anything. But you have different ways to display it. You can look at your tire and say, oh, every 30 seconds it's 12 psi. Not very interesting. But if it's supposed to be a 12. But if it drops to 5, now I need to worry about it. So you have things like stoplights that just bring your attention to that this is something I need to pay attention to. You don't care on a minute-by-minute basis that your tire's the right PSI. You care when it's not. So instead of actually trying to look at that piece of information consistently, you have something to throw it up to bring your attention to it. You have things like the gauges. That's much easier to read visually than having to know that you're doing 110 miles an hour so far. If you want to review historic data, a chart is much easier. A chart like this is much easier than going back and remembering 10, 11, 11, 12, 13, 12, 11. Most people can't do that in their head. But in a little chart, you can easily follow trends and do historical analysis. And so these are just a couple of instances of dashboards that I stole from different places along the web. But to show you some of the things, you have things like the low warning light. You don't care what the actual pressure is. It's just something to bring your attention to that there's a low warning. You have the speed, you have colors. There are lots of ways to bring your attention to data or to use data that's not just numbers, but is equally valid as the numbers. Okay, and so this is, if you saw this presentation last year, I went into more detail of what I would do. And I will give the standard disclaimer, there is no right answer. This is mine, based on my experience. This is not endorsed by the Solar Car Challenge. This is not anyone else's other than mine. So if I were doing this system, the very minimum number of things that I would want is the array current, motor current, I put the brake in the wrong place, battery current, speed, array voltage, and throttle positions, brake positions. Why do I want those? Because I want to know the health of my battery. I want to know what's going on with my solar array. I want to know how fast I'm going, because that gives me the ability to do trend analysis. The odd one in there is the throttle position. And this goes back to what I said about drivers. There are multiple ways to drive a solar car which have vastly different results. If you want to go 35 miles an hour, you can slam the gas down, get to 35 miles an hour very quickly. Oh, I'm at 35 miles an hour, take your foot off the gas. Oh, I'm going too slow, slam the gas down. That is an incredibly inefficient way to drive. But unless you're sitting in the car with the driver, you have no idea that they're doing that. But if you know the throttle position, it's very easy to go back and look at it and train your driver as to, hey, you need to slightly apply the gas and hold it consistently, and this is how you do it. Train him. And you need the most important one on there is the current. I broke out the individual currents because that tells you the health of your array and what's going to your motor. But you need to know, the most important thing you need to know in a solar car is the overall current going into and out of the batteries, because that tells you how much fuel you have in the car. Some of the more advanced things, I really want to know the weather, because that's what leads me to decisions on how I'm going to run for the day. I want to know the weight of my car and the profile of the road. If I'm going uphill and downhill, you can make very simple models. I use Excel for this, of how much energy I'm expecting to use. And that can lead me to decisions of, am I going to run this section or am I going to trailer it? The sensors that I would use. I'm a big fan of Hall effect sensors. They're much more complicated than using the shunts that most people use. However, they're a closed system. You don't actually have to tap into the high voltage line, which I'm a fan of. They have some drawbacks. They tend to have thermal drift, so you have to be able to compensate for that. You have to calibrate them occasionally to make sure that they are actually accurate. But again, you don't have a high voltage connection floating around in there. Voltage, analog to digital converters, any ADC chip. I'm using it's called MCP 3208. There's a whole bunch of them. I'm actually probably going to change to a Texas Instrument chip here shortly. Kind of. I want the throttle positions. I'm going to grab that with a pinchiometer because that's the easiest way to do it. And I really like, as someone said earlier, I really like using GPS for speed. It's simple, it's quick, and can give you a lot of information. So there are many options when you build the system. I have, on the table up here, you've seen, I have 3 systems that I have built. There are 2 based on the Arduino and 1 based on the PyTop. They're also commercial systems. Houston has an incredible data acquisition system that's sponsored. It is an absolutely amazing system. However, and they're sponsored, if you had to go out and buy it, that's a $12,000 system. So there are trade-offs in all of those. And I said, there is no right way to do this. It's based on what you're interested in and what your budget is. That being said, a month or so ago, I was given a new toy. So we're going to talk about this one because I think there's a lot of potential in the PyTop to be used in telemetry. And I have really enjoyed developing this, so we're going to share it with you. So I started out doing Arduinos, which are very nice little toys, but they're slow. I have one that's running 16 kilohertz and one that's running, or 16 megahertz, and one that's running 48 megahertz. The Raspberry Pi is running 1.2 gigahertz. It's got 1 gigabyte of RAM, 8 gigs of storage, Wi-Fi, Bluetooth, and USB, and 24 general purpose input outputs. Basically what that translates into in English is it gives you a lot of capability to do things that you're interested in. You can put sensors, you put a lot of sensors, you have a lot of options on sensors that you can put into it. You have a lot of processing that you can do on the computer. An Arduino, and even most of your commercial systems, are not going to do the processing on board. They're going to record the data, give it to you, and expect you to process it somewhere else. The PyTop has that ability to process it for you and display it for you. It also, on that display, it has a really nice 14-inch HD screen, keyboard, and it has really good battery life, which I have appreciated a lot. So with the kit they're going to give you, you have everything that you need to build a PyTop. I went with an off-board chip. However, they give you a chip on an analog to digital converter on this board. I don't like that board because for an actual solar car because it's not permanent, and I really don't want 96-volt line popping out at the wrong time. It could be really bad. So I went and bought a $3 analog to digital converter. So for $3, you can build yourself a very good, very capable telemetry system out of this, and everything else the folks at PyTop are going to give you. So I think that's an incredible opportunity, whereas my Arduino systems are averaging between averaging about $200 a pop. So I use the prototype shield here, and I'll see a picture of it later on. Okay, so one of the drawbacks for a PyTop is that PyTops run at 5 volts. If you put more than 5 volts into a PyTop, it's going to burst into flames. Not literally, but it will let the magic smoke out, and once the magic smoke is out, it is really hard to get back into the equipment. So how do you measure something that's running at 48 or 98 volts? There's a really simple circuit that involves 2 resistors that basically allows you to measure any voltage that you want. You could use the system to measure 1,000 volts if you were so desired and very brave.
But we're not going to have 1,000 volts in a solar car.
I said you could, not that you are or you're going to.
Is that in the rules? Is that challenging?
No, no, that is not a challenge.
So how you pick those 2 resistors basically allows you to measure any system. And they're resistors. They're cheap. You can buy 100 resistors for 20 cents. So you can pick one. And that allows you to scale your voltage into the range that the PyTop can deal with, or the analog to digital converter deals with. Okay, so this is my system. You have Raspberry Pi over here. You have the PyTop integration board, and then you have the analog to digital converter. A couple things I'll point out is, you notice the wires are all done, bundled up and clean. Proper wiring is important. It's very helpful to keep track of what you're doing. You don't want a rat's nest running around in this, especially if you're running in high voltage systems. So I have that's my little analog to digital converter. It's a MCP3208 microprocessor. It costs $3. I bought mine, because I live in Hawaii, I bought mine on Amazon, and I paid an exorbitant $3.50 to ship it to Hawaii. But most people don't have that problem. The reason I like it is it's a 12-bit analog to digital. So basically, its precision allows you to break it into 4,056 individual steps, which it's 5 volts divided by 456 steps. It is basically the minimum resolution of that sensor, which is more than enough to any solar car system that we're going to deal with. It's running Python, and Python is a wonderful system because everything is available. It is very rare that you are a pioneer who is doing the first thing that anyone has ever done. You might be doing something different, but you can steal other people's code and adapt it to do your specific purpose. So there's a library for this chip out there. I'm a mechanical engineer, as I said in my background. I'm not a programmer. I don't actually know how to go to the system level to make this chip read it. But I can go on the internet, download the library, and write the 3 lines of code that makes it read. So I really like it. And it uses SPI communications, which is a communication protocol. It uses 4 pins on the Raspberry Pi. That leaves you 22 other pins that you could do other things with. Oh, and the warning note, if you're running battery voltages into this thing, this is a high voltage system. As I made the joke about the magic smoke, it needs to be respected as a high voltage system. The lead wire that goes into the batteries can do bad things if it's not respected. So protect it and treat it like you would your battery wires. Some of the speed options, GPS. So I'm a big fan of GPS. You can plug a USB port in. You could add another chip to that prototype board to read a serial as an actual chip, as a very cheap option on how to do it. I've got a GPS antenna over there on the table to show anyone who's interested. Michael also has a system that he's going to show later on to measure your wheel speed by basically interrupting a beam of light to accurately measure your speeds. You have lots of options. You can also put a potentiometer and measure how fast it's changing. You have options. That's the beautiful thing about this. Okay, communications. You have options in this. You can do your analysis on the PyTop. The PyTop, depending on how your car is, it may or may not be a great idea to have a laptop sitting in your car. So you have options. You can do the analysis on the PyTop right there if you can fit it in your car. I'm pretty sure the PyTop folks would not be too offended if you hack up their pretty little case and use their screen and their integrator board in some inventive ways. I already talked to their engineer. You can stop staring at them. But yeah, so you can integrate this into the dashboard of your car if you're so inclined. If you're a solar electric car, the passenger might have the time to sit there and read it. And so you can use that 14-inch display. You also have options to get this data into your chase vehicles. We have the picture I have on the screen is a LoRa radio. They're 900 megahertz radios. They're good to about a half mile. I've got one up there. I've been testing them and using them. They work pretty well. The Raspberry Pi also has a built-in Wi-Fi. So you could either pair it to a cell phone and stream it through that way, or if you had a nice powerful access point and directional antenna, you could probably stream directly to an access point in the chase vehicle. We've also had teams use ham radios. If you want to do packet radio on hams, you have lots of options to get this data off onto a base station so that the people in your pits or your chase vehicle can do the analysis and allow your driver to focus on driving, which is his or her primary purpose in life, and they should be. Thanks. Okay. So software. We developed a very quick piece of software that allows you to display the very most basic things. Basically, right now it's displaying the main voltage, auxiliary voltage, the current, and your amp hours. So basically it takes the place of an e-meter and shows you the basic voltages. This is available on our website right now so that you can use this basic tool. But we really don't want you to end with this tool. This is the basic. We're giving you the tools to go out and build something spectacular. We really want to challenge you to take our example or go completely different and build something for yourself. But we use Python because it's native to Linux and to the Raspberry, and as I said earlier, it's a very powerful language. It's also very simple. It's very straightforward and easy to learn, and there are many resources available to help. So this program also streams the data into an Excel file so that you can go back and read it later and do your analysis and see what your drivers are doing, train your drivers, show them where things went good, things went bad, things were ugly. So as I said, this is available right now, and will be available. It's fully commented so that you can, even if you don't really understand Python, you should be able to go through and kind of puzzle out what's going on and hopefully expand on it. And then, as I said earlier, there are resources available, including the community board, and to reach out to the staff for help, for assistance. So this is one that I wrote. This runs on Windows. I haven't gotten it working on the PyTop yet, but this is an example of one of the things you can do. This is a much prettier dashboard that has gauges and things. It's much easier to process the data than just the raw numbers. So there are probably many students in this room who are much better programmers than I am. So I have faith that there are going to be some amazing systems that are much better than the very basic things that I put together over here. Okay, so our software is available online. We have a page on GitHub. They have been kind enough to give us, to assist us with our repository. So this is where we're dumping the code and also the schematics that you need to start putting these things together. These are not going to work out of the box. They are going to require some effort on your part. We built the scaffolding to help you build the product. You still require some work on your part. But you should be able to measure voltage and current almost out of the box. There is lots of room for future development. Real-time graphing, gauges. You are limited by your imagination and what you can do. There are other options of how you can expand this project. One of the things is you're required to have an audible low voltage alarm. Well, we're measuring voltage. We have a speaker. I bet you could connect those two and make yourself a low voltage alarm. I don't know. I mean, one of the things we consistently have arguments about on cross-country races is, did the driver turn on the blinkers? You could monitor the blinkers. That would be a very simple thing to do. Display for the driver, pull up the logs. Yep, see, blinkers right here. There are an infinite number of other sensors you could add. You could add cruise control for the closed track events. This goes back to how the driver drives. You could make a very efficient model of how to drive a solar car for the closed track events. Okay, I'm going to drive 10 miles an hour, 20 miles an hour. I want to drive at 50 amps, set it. Let the car drive itself in the most efficient manner. Or current speed minder. If you're familiar with NASCAR, they have a little button they push when they go on the pit road so they can't overspeed. You could do the same thing for our pit road, or for the road. Set your speed on the tracks or on the cross-country event so you can't speed. I don't know if it's useful or not, but it's an option. There are lots of options, and that's the other part I'm going to say. And really want to encourage you to come develop them. And we also want to encourage you to share them with others. The GitHub page, you can fork our code, steal it, but we encourage you to share what you've done with others so that other people can learn from your experience and help the other teams. Do we have any questions? And I put the links to the resources on the bottom so that you can find them from the web page. Questions?
You did 2 good jobs.
I either bore them to death or oh.
Okay, so my one question is, so you've done consulting for, can everyone hear me?
Yes.
Okay, great. So you've done consulting for some of the solar car teams.
Yeah.
You've done consulting for others, I'm assuming?
Yes.
You said you were a naval officer, correct?
Yes.
So what other types of projects have you worked on that required large amounts of data?
I worked on, when I was in college, I worked on the drivetrain for the Tesla. The first generation Elise had a really annoying habit of blowing up its gearboxes. Kind of really annoying, especially with our $120,000 car. So we spent a lot of time working in the Georgia Tech Research Institute, had the contract to help with the development of how not to blow up a gearbox. And that, while it seems very simple, it went into collecting a lot of data on the torque, how torque is applied, the rate at which torque is applied, and things like that. I also worked on a DARPA challenge for the next generation Humvee, which is a diesel electric hybrid. And the efficiency models on that required 1 hour run generated almost 4 gigabytes of data. Lots of data. So this is one of those things that some people find this to be the most boring thing in the world. If this is something that interests you, this is a great career. There are people who love to pay you money if you can understand how to analyze data. This is something Amazon, if you will throw money at you to do. One of the guys I work with just retired, and he's now working at a processing center doing exactly this. Collecting data, analyzing data, and displaying it so they can optimize their organization. And he's making about $200,000 a year.
How many sensors is too many?
Oh, that's a very difficult question. The too many sensors is the point where you no longer are getting useful data from them. As long as you can physically support them and you can use them, there is no such thing as too many sensors.
So your auxiliary battery pack's bigger than your main contact.
All right, Jarrett, can I offer a counterpoint? Since Jarrett very much likes getting everything he can get his hands on. Having spent a fair time doing data analysis myself, I can tell you you want to be careful because you can get bogged down in the details. You can have so much information coming in that you are so low to the ground you completely miss the big picture. I strongly recommend starting off simple with the big stuff, like the key things that Jarrett focuses on. Above all, knowing what's going in and out of your battery pack and system voltage. I mean, even if you just start with those two things, you can trend it over the time that you've run. Then start building on that. And you get, because if you just start trying to trend everything else, it's like, well, you know, if I look at the temperature of the cockpit and I kind of cross how steep the hill was, it kind of plays into what the driver was doing with their foot, but as opposed to, well, look, here's where our current draw was a hill. Well, it's kind of what we expected. So, just cautionary.
Yes.
Start off basic, build from that.
Yes, and you're also limited by your ability to process that data, and that's unless you happen to have a server farm. That it is definitely possible to have too much information.
Have you all tried connecting a Raspberry Pi to an Alltrax to get the information straight from there? Is that where it does?
Actually, that's one of the things I should have mentioned. No, we have not actually done that, but that is one of the options. Alltrax for controllers, Midnight Solar for your power trackers, Bursa for power trackers, and if anyone's still running NGMs, all have serial lines out that give you an exorbitant amount of information about how that system is working. You can feed all that into your telemetry system, and potentially should, so that you can get information. And you can go back and actually read the numbers, pull currents out, or just have we call them the idiot light, the red light that comes on when it's too hot. All of those are things that you can do, and things that would be great things to explore doing.
In the beginning, you talked about troubleshooting. What exactly does that entail?
So, troubleshooting for cars, it depends on what's broken. Basically what I do for a team, when teams are in that desperate straits, they tend to be jumping around, looking at different pieces, and not doing one holistic view of it. Basically what I do is I'll show up and say, okay, what's your problem? Okay, well, let's start at this point. What's this supposed to be doing? And working your way through it in a systematic approach. Start at A, go from A to B, B to C, and work your way through it systematically until you identify what the problem is and what you need to do about it.
Do you want examples?
Sure.
So,
Once you do, I've got one.
all right. So examples that I've seen with teams, we have random voltage on the frame that we don't know where it's coming from. That'll prevent you from getting through scrutineering. The car starts and then immediately shuts off. We don't know why. Our array, we don't know whether it's actually putting power out to the batteries or not. Our battery pack, we're actually not sure what's going on with that. It was at one voltage, now it's at something else, and the car just doesn't seem to be running right. Those are the kind of things, especially with new teams, that sometimes, if you hadn't had the opportunity to drive test beforehand, you encounter when you get to the track. You encounter when you do it for the first time, or you encounter when you actually start stressing the components. And those are the type of things that Jarrett will come and help guide you guys through your process to figure out what it is. 'Cause it's easy when you've got this entire system put together to get lost in it.
Yeah. We're not going to fix your car. That's on you.
I've got to add one thing. As you do more with solar car, you become more sophisticated. You start approaching things from avenues like you're talking about, and like you're talking about, that deal with checking certain things and looking and all that kind of stuff. But when you're new to solar car, you use sometimes more basic approaches. And our next presenter is going to be my best example for that. We had a short to the frame of our solar car. We came down to Austin so that we would be able to have a New York Times reporter cover us and all that kind of stuff, but we couldn't run it because of the short. But this fine young man donated his body to help us figure out where the short was, because he went through the car going until he went, ow! And that's how we found the short. So ever since then, we call him Sparky. That's not what I recommended you do. But when you're young and you're a new team and you're not really sure what to do, sometimes innovation's not a bad thing.
And I'll give my story, my favorite story, because it involves a staff member and I love to pick on him. There was a car that we had that would not charge its batteries. Could not figure out why. They replaced the battery pack in the middle of the race, took the penalty, kept trying to work on why their solar car wouldn't work. So, okay, and they were testing different things, doing different things. Was the power tracker, was it the array? Didn't have a real systematic way in which he was approaching it. He's a mechanical guy, not an electrical guy, to be fair to him, as he knows who I'm talking about over there. So we started, okay, well, if you're not charging the battery, are you getting electricity from your array? That's the first place to start, okay? Start at the array. Yep, there is power coming into the array, okay? Next thing, power tracker. Is power going into the power tracker? Yep, power is going into the power tracker. Okay, is power coming out of the power tracker? Yep, power is coming out of the power tracker. Okay, the next thing is the switch. Is power coming into the switch? Yep. Is there continuity across the switch? Yep. Okay, is power coming out of the switch? Yep. Okay, well, why isn't power going into the batteries? Okay, well, let's follow this wire. There's only one other place you can go. We follow the wire, and lo and behold, the wire is not attached to the batteries. So that's an example of how you systematically troubleshoot, where you can jump back and forth between individual components, check the fuse, check the battery voltage, check the individual cell voltages, check the battery again, blame the power tracker and troubleshoot the power tracker for a while. But the systematic approach finds the problem. Any other questions?
Let's take a break now and stretch, and then come back and listen to Michael.
Guys, we're going to take a break, and when we're done with the short break,
So yeah, just take 5 minutes. You can get on stretching your legs.